Okay. Now, pressure meters. What type of pressure sensors do we know of? What type of pressure sensors can you think of? Yeah, now, we've got pressure sensors with a diaphragm. How are we going to measure the displacement of that diaphragm? Piezo. There are two types of piezo. Piezoelectric and piezo resistive. Strain tube. Yes. Now, strain gauge. That's used on load cells, and it's usually used to measure weight. Bourdon tube. That's used on just gauges, the sort of thing. Jeffrey, have you got a question?
I've noticed before when you're talking about flow, and I was talking to one of my family members over in the United States, and apparently they use the principle of the turbine meter to actually generate electricity in the ocean. Would that actually get the same sort of problems like the meter would, or not really?
No, not really. We'll talk about that afterwards, if that's okay. Remind me to talk about it after when we do tutorial time. Okay, any more types of... somebody said capacitance. Well done. Capacitance. Okay, now over the years, there have been lots of other different types of pressure sensors, and they've come and gone, thank God, because most of them were absolute rubbish. Nowadays, there are three basic types. If we put strain to one side for a moment, there are three basic types of sensor we use. The capacitance type, and the two piezo types. As far as capacitance goes, we'll probably use, instead of just a straight old type metal capacitance cell, nowadays, for the last 26 years, we've used ceramic capacitance. Well, anyway, for the last 26 years in the rest of the world, maybe in WA we'll be catching up soon. So, for about the last 26 years, we've been using ceramic capacitance, and that's called Cerebar by Endress and Hauser. It's called a Vega bar by Vega, and I don't know what it's called by anyone else. Rosemount probably call it some crazy idea that they'll be thinking about in 20 years' time, because they seem to be a bit behind. So we're using ceramic capacitance or one of the piezoelectric or piezoresistive type sensors. When it comes to choosing pressure sensors, this is the thinking I go through. I say to myself, is it over 400 degrees C? If it's not over 400 degrees C, if it's less than 400 degrees C, I'm going to use ceramic capacitor. Now, ceramic capacitor is the diaphragm type 1. What we have is we have a very thin ceramic diaphragm and another diaphragm, and then we have a hole through there actually. There, like that. And there are two capacitive plates, one capacitive plate there and one capacitive plate there, and we measure the capacitance, the movement between those two capacitive plates. The ceramic diaphragm moves by nanometers, which means about the size of a gnat's thingy. So it doesn't move very much. They're very solid. So if at all possible, I'm going to go Cerabar. That's going to be my first choice, unless it's incredibly hot. If it's incredibly hot, if it's a static pressure I'm looking at, then I'm going to use piezoresistive. If it's a non-static pressure, something like a vibration, I'm going to use piezoelectric. Piezoelectric is not so good at static pressures because piezoelectric only measures changes in pressure. So my second choice will be piezoresistive. If I'm going very, very high pressures, very, very high temperatures, I'm going to go with piezoresistive. But anything less than 400 degrees C, I'm going to go Cerabar. So here we have my steam pressure coming in. And I need you to choose. What would you choose as a pressure sensor?
I was looking for that. I was looking for that.
Oh, looks like you found it. Now think carefully. Steam. How hot is steam going to be? Is it going to be over 400 degrees C? Okay, now, it seems the majority of you have plumped for piezoelectric. Piezoelectric is the one we would use if we have high pressures and we're measuring something which is changing a lot. Changing very quickly and, well, a lot. If we have high pressures and high temperatures, we would go for piezoresistive. Pneumatic DP, forget about that. Manometer, we're not going to do that one. We're not going pneumatic because, well, that's the sort of thing we used to do in the last century. Ceramic capacitance, now that is good up to, let's get a better pen color, up to 400 degrees C. Okay, so being as the steam is only going to be somewhere 100 to 110 degrees C, I'm probably not going to get much more than 10 degrees of superheat in my steam, then I'm going to go for the ceramic capacitance. The reasoning is because it's accurate and it's cheap. They are very cheap. They're very reasonably priced. No, the ovens... yeah, I take your point. No, the oven's not actually that hot. Although it does get quite hot, because although the steam is only coming in at 110, I actually managed to get more than that temperature out of it, because I'm not getting temperature, I'm not creating heat by taking steam at 110 degrees, or even water at... If I was to take water... Oh, hang on, let's start that again, start the whole sentence again. If I take steam at 100 degrees C, or 110 degrees C, and I change it into steam at 100 degrees C, I get energy out. I get some energy out. However, if I take steam at, a bit more space here, steam at 100 degrees C and I turn it into water at 100 degrees C, then I get loads of energy out. So what I'm actually doing is I'm putting steam into the oven and I'm taking condensate out. And so I'm actually generating more heat than you might expect. So my oven is getting good and hot, thank you very much. So by changing steam into water, I generate an awful lot of heat. Because what I'm doing here is I'm liberating the hidden heat from the steam. Okay, now I want to measure the temperature of my ovens. Some suggestions for temperature sensors, please. So I've got thermocouple, which is 2 different types of metal. I think what you're talking about there is infrared pyrometry. Okay, infrared. Infrared, and what infrared is really good for is non-contact. Now, when we talked about infrared, then we did mention the infrared sensors, unless you correctly set up the emissivity, then what you end up reading with an infrared pyrometry is actually the color of the object and the surface. I also have some people have told me RTD, resistance temperature devices. There are 2 types of RTD. There's the ones that are a piece of wire, piece of platinum wire typically, that's 100 ohms at 0 degrees C. Anybody know what that one is called? So I've got platinum wire, platinum, and then we have the thermistor. Thermistor, platinum wire, which is called the PT100. So I have the PT100, the thermistor, IR pyrometry, and the thermocouple. And these are the choices I have for temperature sensors. Here's the way my thinking goes with temperature sensors. If the temperature is less than 100 degrees C, and I don't want special accuracy, so, you know, within a degree is good enough, then I'm going to use a thermistor, because a thermistor is as cheap as chips. Thermistors are horrendously cheap. They're so cheap it's just not funny. So unless there's a good reason, you know, if it's less than 100 degrees C and I don't need great accuracy, I'm going to use a thermistor. If it's more than that and I need better accuracy, if I need fabulous accuracy and I don't care about the expense, then I'm going to use a thermocouple. Thermocouples are expensive to install and they're expensive to maintain. So if I need great accuracy and hang the expense, I'm going to use a thermocouple. However, if I need reasonable accuracy, then I'm going to use a PT100. So that's my thinking. If I don't care about the temperature that much, I'm going to use a thermistor. If I do care and I want great accuracy, thermocouple, but if I want good accuracy but not great expense, then the PT100. So here's my choice here. What I'd like you to do is say what you would choose. Well, I think you're right. I reckon it's a toss-up between the PT100 and the thermocouple. And all things considered, I don't need fabulous accuracy. So I think on this occasion, am going to go for the PT100. Okay. That's our basic instruments done. Now, here's a tricky one. I want to measure the weight of the donuts. Who's got suggestions for measuring the weight of that donuts? Aha, the first thing you come up with is a load cell. The load cell idea is a thing called a weightometer. This is a standard way of measuring the weight of stuff on a conveyor belt. What you do is you have a conveyor belt going past, and one section of that conveyor belt is independently sprung. And you put a load cell on that section, and you weigh that section. Now that's fine, and that's absolutely definitely the way we measure stuff on the conveyor belts coming out of mine sites. And that's definitely the way we do it. Except the criteria for this to work is that the stuff on the top must be very much heavier than the belt. Now, unfortunately, in this case, that's not going to work. And any type of weighing system is not going to work in this case, because the donuts really don't weigh very much. The donuts weigh about 100 grams. They're not much heavier. In fact, they're lighter than the conveyor belt they're being carried on. So, I have a problem that I can't weigh them using my standard conveyor belt measuring system of using a weightometer, because the conveyor belt is going to make a bigger difference than that. Okay, volume measurement. Now, if we had an even distribution of donuts across the belt, then we could do some type of volume measurement. Radar. Actually, radar is coming incredibly close to what we will do. Radar is very, very close. The only problem with radar is that radar uses microwaves, and microwave is specifically absorbed by water. So the radar would tend to be measuring the water weight rather than the basis weight. But you are very close. Okay, I'm going to put you out of your misery. We have a saying in instrumentation: when all else fails, nuke it. We use radiation to measure virtually everything. There's frequencies of radiation, you see, that will be specifically absorbed by certain substances. For instance, there are frequencies of radiation which are specifically absorbed by cellulose. So we use those frequencies to measure things like paper weight. So what we do is we put a radioactive source underneath the thing, we put a radiation detector above the thing, and we measure the amount of radiation getting through. And so we put source underneath, detector on the top, and we squirt radiation through the object. And then we measure how much radiation doesn't get through because some of the radiation gets absorbed by the object. So, by measuring the amount of radiation absorbed, or by checking to see how much radiation is being absorbed by the object, we know the weight of that object. We use radiation to measure. We use radiation to. Hang on, I'll just. Now, we use radiation to measure the weight of all sorts of objects. We use radiation to measure the basis weight of paper, the basis weight of glass, plastics, ceramics, anything that's produced on a continuous production line, woven fabrics, non-woven fabrics. Virtually all the clothes you're wearing would have been irradiated. The weight would have been measured using radiation. Any piece of paper you have in front of you, the weight would have been checked using radiation. We use radiation to measure the thickness of chipboard, so that the chipboard is thick enough and it's correct density, and then we use radiation to measure the thickness of the melamine that we put over the chipboard. So we use radiation all the time to measure all sorts of things.
Ain't it bad for food?
No, not actually. No, we actually, you'd be surprised how much people, it doesn't, radiation isn't catching. It's not like we're irradiating the donut enough so that the donut becomes radioactive in its own respect. We're just going to pass a bit of radiation into it, which is just not much higher than natural background radiation. I mean, you take a donut, you sit it out in the sun, and it's getting irradiated. So even food stuff is irradiated. We're using radiation all the time to measure stuff. It's amazing how much stuff we do measure with radiation. When we make tires, we use radiation to count the wires in the tires to make sure that the metal bands in radial tires are in the correct place. When we make cables, you know, normal standard three-core cable, we use radiation to make sure that the insulation is good on the cables. There aren't any bubbles or breaks in the insulation. We're basically using radiation all over the place. And that's something that we have to be aware of as instrument people, because this is us. This is our territory, the radiation. At some point, you may be working on a radiation system, and you may be required to take your radiation supervisor's course, because there's a large part of instrumentation that involves radiation. Okay, so that's the basis weight sensor. We're gonna nuke it. What about the moisture sensor? Anybody got ideas for the moisture sensor? Now, resistivity is a great idea. Resistivity is the way we measure the moisture in a piece of wood. However, it relies on sticking two probes into the donut, and I really don't want to do that. And strangely enough, John, you've hit the nail on the head. We'll nuke it. This time, we'll nuke it with, yeah, we could eat it, but that's, the feedback from eating it is non-electronic, and it's too slow. So what we're going to do instead is we're going to nuke it. There's two frequencies of radiation that detect water, and those two frequencies are infrared and microwave. So what we do is we nuke it with microwaves, and we measure how much microwave gets absorbed, because the more moisture there is there, the more microwave gets absorbed. So once again, we're going to nuke it. So we'll end up with a radioactive source and a radioactive detector and some donuts between. So source, detector. Now at this point you may be getting the idea that there's a bit of radiation around the place. Well, there is. And we have to be very careful of this. It's going to be our purview to be looking after these sensors and gauges, and this is something we need to be aware of. Now, I won't go into the colour because I'm sure as soon as I ask you how to do colour, you're going to tell me to nuke it. In actual fact, nowadays, there are lots and lots of colour sensors on the market, very cheap colour sensors, using the same sort of technology you get in your little, well, cameras, digital cameras and digital video cameras. So there's lots of cheap colour sensors that are very cheap and easy ways of measuring colour. So now the mounting of the sensors. Here's my conveyor belt. My conveyor belt is 3 meters wide. Where shall I put my basis weight, my moisture, and my colour sensors? Where shall I put my sensors? Okay, problem I have is that this is a 3 meter wide belt. If I put it in any one particular place, then what I'll do is I'll measure just the values there. If I put my sensors, if I put them all here on one side, all I'll do is measure the donuts coming through at that side. And what might happen is that the oven is cooking unevenly, and all the donuts on the other side, all the donuts over here, come through uncooked. So I need a way of measuring all of the width of the donuts, the whole width of the belt. I could put a whole load of sensors right across the belt. That is going to be horrendously expensive. That'll be a very expensive exercise. So I need to measure the full width of the belt, but I only want to use one set of sensors. So any ideas? Jeffrey, have you got an idea?
Yeah, could you just use cheaper sensors, but just sort of maybe 3 or 4 of them?
I'd prefer not to. What I'd prefer to do would be to have an accurate sensor, but that is somehow able to measure the entire belt. I'm not able to funnel the whole process into one stream, because they're laying out on my conveyor belt at the moment. I want to measure them on the belt as it is. I think what Eddie's saying is put a sensor over here, or put a transmitter over there, shining across, and a receiver over here. So there's my transmitter, there's my receiver. Now, if we're talking about using a radioactive source as a transmitter, then this is horrendously dangerous. This would never be allowed. Because you're basically squirting radiation out everywhere. That's not, no, I can't see that one being allowed. Now, you're saying use a sample point. Not sure what you're meaning by that. I'll tell you what, I'm going to put you all out of your misery. We use a scanner. We put the sensors in a box and we scan it backwards and forwards across the belt. We use scanners for measuring anything that comes out in a continuous sheet or that comes on a conveyor belt. So these scanners, most of these are paper scanners. This is a Honeywell one here. This is the Honeywell one. And this one is made by ABB. It's called an Accuray scanner. These other ones, this is for measuring plastics. And I think that this one is a metal scanner. But they all use the same principle. We put the instrument package in a box and we move it backwards and forwards using toothed belts. So inside of these scanners we have toothed belts that drive the heads backwards and forwards. And the tooth belts keep the two heads perfectly aligned with each other. Now, as well as using tooth belts to drive that backwards and forwards, we also need some way of getting the cables from the end over here to the scanner over here. Any idea what we use to get the cables and the pipes? We might have air lines going there. What would we use to get the signals from one end? Trailing cables. Yeah, we do use a trailing cable. In fact, we use this thing, it's called, I'll try and draw it. It's called a power track. It looks like tracks on a tractor. They're usually made of plastic, and these tracks all join together. And inside this power track, we put all of our ribbon cables. A drag chain. Yeah, I think it can be called a drag chain. If you know the sort of, I desperately looked for pictures of them to show you, but I couldn't find any. But it's basically, it looks just like a tractor track, but it's hollow, made of plastic, and all the cables and pipes go inside of it. Now, once again, this is our territory. Instrument people will be looking after this. We'll be looking after the pulleys, the belts that go backwards and forwards. We'll be making sure that the belts are the correct tension, because if the belts are not the correct tension, as the heads move backwards and forwards, the radioactive sources, the sources are in the bottom, the radioactive sources come out of line with the receivers. If that happens, then we get bad readings. So we'll be tensioning the belts, making the belts the correct tensions. We'll be checking the drive motors, because there'll be a drive motor driving all this. We'll be checking the power tracks, and you better believe the power tracks go wrong all the time. We'll be checking the pipe work and checking all the other good stuff. Just out of interest, this little box here, that's got two lights on it. It's got a little red light and it's got a little green light. And the little red light says shutter open. What that means is the radiation is on. When the little red light lights up, the radiation is on. If the little red light goes out and the little green light lights up, that means the radiation is off. Now, one issue with these is if you have a radioactive source, let me just make a bit of space. If you have a radioactive source, I'm going to put a source here. Actually, give myself a new page. If I have a radiation source, I'm going to have that source contained inside a box. And that box is going to be opened and closed by a shutter. The little solenoid which opens and closes that shutter, the wiring for that solenoid, blue for wiring. Wiring for that solenoid has to be, by law, in series with the shutter open lamps. So that whenever that shutter is open, the lamps are on. And the lamps are only on, sorry, the shutter is never open if the lamps are not on. Now, you can probably guess what the biggest failure item in this circuit is. Well, yeah, it's the bulbs, and it's very annoying. You get called in all the time, and you go up to the thing and you give it a whack with the back of a screwdriver, and the lamp just comes back in and it's all good. And so the biggest call-out item with this is the lamps, and then just after that it's the solenoid. The source is just a solid radioactive source. That's not going to go wrong.